purple tie.
Yeah, I wore it just for the K-State.
Oh, so cute.
Yeah, just for that.
Sorry, you employees.
Okay, so as we finish up this lab, and a couple of things that you need to keep in mind in terms of what you're ultimately after. Okay, so as you figured out last Friday, that 1 or 2 drops of base can make a huge difference in that pH curve. Okay, so you're going along, okay, adding it, then all of a sudden, bam, you hit that spike, okay? And this is the whole quality of this lab boils down to the exact values and those pHs that correspond with that spike. That's the most important thing. So here's what you're ultimately after. Then the only way you can do this is to look at the graph, okay? That's it. You cannot do any of the calculations until you get the graph. So let's say your graph looks like this. So what you want to do is you want to come in here and you're just going to have to guess, okay? You just have to all eyeball. And you're going to guess kind of where the midpoint of that curve is. This is why you have to have such good data. So you're going to kind of guess the midpoint of that curve and that volume. Evan?
Is it the midpoint of the curve or is it 7?
No, it is not 7. It is absolutely not 7. It is absolutely not 7, and I'll show you why in just a second. Okay? It's not 7. It should be above 7, actually. Okay?
Okay, that's good. That's above 7.
Yes. But you don't need the pH at the equivalence point. Okay, this is what we call the equivalence point. The only thing you need at the equivalence point is the volume. Okay? So I'm just going to make up a number. Let's say that was 26 milliliters. That's the only thing you need at the equivalence point. Now, the reason that you need that is because you're ultimately after 2 things about this acid. You're after the molarity of the acid, and you're after the Ka value of this acid. Okay, that's what you're trying to find. So you're going to use this volume here in MAVA equals MVVB. Okay, so what you're trying to solve for is the molarity of the acid. You're going to know the volume of the acid. You're going to add exactly 25 milliliters of your acetic acid. That's why we use that volumetric pipette. So you will know the exact volume of that acid. You're going to know the molarity of the base. That's what you found last week. Okay, so that's going to be that average molarity, hopefully something around 0.1. Okay? And you're going to know that to 4 significant digits. So you're going to know a very precise measurement of the molarity of that base. The volume of the base is going to come from the midpoint of that curve. Okay? So you're going to know the molarity of the base, the volume of the base, and the volume of the acid. The only thing you're not going to know is the molarity of the acid. So divide that over, boom, there you go. Okay? And you're going to do that 3 different times. So that's the first thing that you're going to find is the molarity of the acid. So that's what's going to go here on this blue sheet where you have molarity of the unknown acid, okay? And again, I don't have to see all 3 calculations, but show me one complete set of calculations about how you got the molarity of that acid. Then you're going to find the average, then you're going to find that standard deviation. Make sure that you show me how you find that standard deviation down below, because it's that same formula that we used before. It's the average minus the trial squared, and then you're going to find the sum of that, and you divide by 2. Now, that's the first thing that you need to do. Now, the other part you're going to need to do, and this is what's going to happen on yonder yellow sheet, where you all have filled in all the data with the pHs. So, to get your volume at 1/2 the equivalence point. So, your equivalence point in this situation, in my example, is 26. So, half the equivalence point is going to be 13 milliliters. So you're gonna go to whatever half that is at the equivalence point. You're gonna draw a line straight down, okay, with a ruler, okay? With a ruler, you're gonna go straight down. Then you're gonna come over here and you're gonna find out where it crosses that pH curve. And then you're gonna come over here and you're gonna figure out what that pH is at half the equivalence point, okay? So let's say that's 4.50, whatever it is, okay? Whatever that is. So you're gonna know your equivalence point, so you need 3 bits of data off of this graph. You need the volume at the equivalence point, you need the volume at half the equivalence point, and then you need the pH at half the equivalence point. So those are the 3 things that you need off of this graph. So the magic happens, and it only happens at half the equivalence point, okay? So at half the equivalence point, we're going to use one option is to use this Henderson-Hasselbalch equation, okay? Log of your anion concentration over the concentration of the acid. So this is on your equation sheet, okay? We're going to use this equation a lot. Embrace it. It's going to become your friend, okay? It's called the Henderson-Hasselbalch equation. It only works with weak acids, okay? It doesn't work with strong acid because there is no Ka of strong acid. So don't try and use this with like hydrochloric acid or nitric acid or something like that. It won't work, okay? It only works with strong acids. Now, with weak acids. So here's the deal. At half the equivalence point, okay? Half the equivalence point. This is what I want you to see about what's happening inside this beaker. So inside this beaker, you all have acetic acid. To really get this, you have to understand the molecular level about what's taking place. So when you first add this, you have the molecular form of the acid, okay? It ionizes a little bit, about 3%, not very much at all. The vast majority of this thing is existing as the molecular form, okay? And you got some hydronium ions and you got some C2H3O2 anions, okay? You got a little bit of this, not very much. Most of it's in the molecular form because it's a weak acid, okay? So what's going to happen is that you're going to add sodium hydroxide, okay? So here's what's going to happen with the hydroxide. The hydroxide ion is going to come in here and goes, yo, mind if I dance with your proton? And the acetate's going to go, yeah, take it. I don't care. I'm really not that fond of it anyway. Go ahead and take it, okay? So the hydroxide is going to react with the acid, the molecular form of the acid, and you're going to make water and some more of that anion, okay? So there's two potential sources for the anion in this reaction. It can either come from the ionization of the acid itself, which isn't going to produce very much, or you can get it from the reaction between the hydroxide and the acid, okay? So the hydroxide is really strong base, and it comes up and goes, yo. The acid goes, take the proton, just leave me alone. And the anion goes off by itself and goes, okay. So what's going to happen is that if you were to look at concentration versus time, I want to look at 2 different things. We're going to look at the concentration of the acid itself, okay? And we're going to look at the concentration of the anion, okay? So as this reaction progresses, as you add more and more hydroxide, what's going to happen to the concentration of the anions?
Increase.
It's going to increase because it's a product of the reaction between the acid and the hydroxide. So the concentration of my anions is going to go up. What's going to happen to the concentration of my acid? It's going to go down because it's getting used up with the hydroxide. So this is going to go down. So at some point, at half the equivalence point, those 2 concentrations are equal. And that's where the magic happens, okay? And this only happens, listen to me, at half the equivalence point. So what happens, if you go back up to this Henderson-Hasselbalch equation, at some point, when it's half neutralized, the anion concentration is going to equal the concentration of the acid. Okay? So prior to that point, the concentration of the acid was bigger than the concentration of the anion. But over a period of time, this concentration goes up, this concentration goes down. Now, at half the equivalence point, that's where the magic is. Half the equivalence point, these two values are equal. What's the log of 1? 0. So at half the equivalence point, you're taking the log of 0, or log of 1, which is equal to 0. So guess what? At that point, the pH equals your pKa. Okay? But it only works at half the equivalence point. Okay? It's the key thing. Only at half the equivalence point. So what's going to happen is that you're going to come over here and you're going to find that half the equivalence point. 13 milliliters. You're going to take a ruler and you're going to draw a line straight up. You're going to come up over here, you're going to draw a horizontal line, and you're going to find the pH of that half the equivalence point. So, where it says here, your pKa, that's your pH at half the equivalence point. Okay, that's what you're going to have. Then to get the Ka, if your pH equals your pKa, which it does at half the equivalence point, and let's say that's 4.30, so that equals 4.30. So how am I going to get my Ka value? How are you going to undo the negative log? Evan?
So you take 10 and you put it to the negative pH power?
Yes. So you're going to take 10 and raise that to the negative 4.3, or whatever you get at half the equivalence point. Yes?
And what is the Ka value for acetic acid?
That's what you're trying to find.
Okay.
That's the whole point.
Yeah,
You're trying to find an experimental value for the Ka of acetic acid. Or you can look it up in the back of your book. Okay? It's 1.8 times 10 to the negative 50.
okay.
Okay? That's the accepted value for the Ka of acetic acid. So, obviously, any small changes in your graph are going to play out large in terms of that pH value. Now, let's go back to something that Evan asked about, hey, what's going to happen to pH? So what I have here is I have 2 beakers of distilled water, okay, and this cheap little pH probe. It's reading about 6.5. So to the first one, I'm going to add sodium chloride, okay? So otherwise known as salt. So I'm going to take this. This is so highly imprecise, but you're going to get the idea. So I'm going to take some salt, and I'm going to add that to this solution, and I'm going to do something that you don't want to do, and use your pH probe as a stirrer. And anyway, so you do that, and the pH basically stays the exact same, okay? Basically stays the same. Now, here's why. So if you look at what's happening, we're going to focus on the chloride ion. So, now listen to me very carefully. Is the chloride ion the conjugate base off of a strong acid or a weak acid? Strong. Why? No, you're making this difficult. Do not make this difficult. Chloride is the conjugate base off of which acid?
Ionized.
Hydrochloric acid.
Hydrochloric acid, yes, that's all you had to say was hydrochloric acid. Okay, now, this is where it turns into a logic problem. Now, does the chloride ion have any attraction for hydronium ions?
No.
No, that's what makes it a strong acid. So the chloride ion, when I put that in water, still exists as water and the chloride ion. Okay? There's no reaction between the chloride and the water. This chloride is going to go up to the water and go, so kind of attracted to the chlorine, you know, kind of attracted to the water molecule, not much. It's like, so I'm negative, you're positive. How are you? And that's going to be the extent of the conversation. Okay? However, Now I'm going to take sodium acetate, also a salt, also a white powder. And now I'm going to put the sodium acetate in water. Okay? And now we're going to see what's going to happen. So, I'm going to take about the same amount. Again, this is so imprecise. Okay? I'm going to put that in there. And then I'm going to give that a stir with my pH probe, which is something you shouldn't do. But now this pH goes up to about 7.70. So when I put the chloride ion in the water, nothing happened. The pH didn't change. I put the acetate ion in the water, and the pH went up. So what's the only way that I can make the pH go up? What am I generating? Hydroxide ions. So look what happens. The acetate is the conjugate base off of a weak acid, acetic acid. So when I put this in there, this comes up to the water and goes, yo, give up a proton. And the water goes, hey, fine. I don't want any trouble. Take some protons. So what's going to happen is that you're going to form some of that acetic acid, but more importantly, you're going to generate hydroxide ions. Once you generate hydroxide ions, what happens to the pH? Goes up. So if the conjugate base, and this is why you need to know your strong acids, if the conjugate base comes from a strong acid, you put it in water, nothing happens. That's what makes it a strong acid. It isn't attracted to the protons. But you put the conjugate base of a weak acid in water, then it goes up and it says, man, Lonely Heart Club, I'm in desperate need to hook up with the proton. Okay? Water sweeps right, and it hooks up with the acetate, and then the hydroxide is left over, and it's going, hell, isn't this just grand? I'm just going to hang out here by myself. So, that's what's going to happen. All right, I am done. So what you need to focus on today, get the data for the two trials. Okay? You got lots of graphs to draw. Use rulers.
So we need 3 graphs.
You need 3 graphs. You need 1 for each trial.
No, it's okay.
Zach? Is that Evan?
What would you consider a good experimental error for this experiment?
30%.
Yeah, 47.
That was just after the first trial, though, you know?
We got 30.
Yeah. Okay. Are we good? Let's go do science.